Ben geçerekten.
Okay, the recording has started. Tahsin Hocam, the stage is yours. Thank you so much.
Thank you very much for everything, for organization, for invitation, and yeah, just congratulations for such a wonderful meeting, and I hope it will turn to a tradition. And honestly, what I will do is basically, I have three different slide sets basically, and depending on the time, I will switch from one to other. And the thing is, I will check the just the audience basically. Some parts may be too easy for some of the participants. Some parts maybe provides further detail for the let's say higher curvature and derivative gravity theories practitioners, let's say. But just I hope everybody finds something that he or she will enjoy. And starting with higher curvature and derivative theories, basically, just starting from the very basics, honestly, and go towards to the things that I work on. Giving a start, and first, just it has three parts. Overlapping parts also exist in these three presentations, but starting from the very first and starting from the very basics of Einstein's gravity, modifying gravity, and why we are modifying gravity. How to analyze modified gravity theories is another thing that I will try to discuss. Equivalent linear action principle. Born-in-fact gravity theories in 4 dimensions is the next thing that I will discuss. And Curvature-Kund class of metrics is solutions to higher curvature and derivative gravity theories. And I will provide a conclusion for the first part and then move to, if time permits, the other parts. Honestly, this is, what I will present is my personal journey related to higher curvature and derivative gravity theories. And to be honest, just a, let's say, personal perspective. But as far as I see, there are several people working on modified gravity theories and providing some info to the student level participants. Just at least, this talk will provide my personal perspective, but other perspectives also possible, and provide a, let's say, a total view in terms of modifying gravity. And these, whatever I will present is basically a work of, a work together with İbrahim Güllü, Metin Gürses, Sigbjørn Hervik, and Bayram Tekin. Also, we haven't just finished up, but I shall mention Çetin Şentürk, also collaborator, maybe not exist in this part of the talk, but in other parts. Just first of all, honestly, starting from the very basics, but hopefully build up quickly. Gravity is an what is gravity is the first thing that I want to discuss. Gravity is an effect a massive object creates on another massive object. And how is the thing? Basically, just for centuries, we answered the thing with the perspective of Newton's gravity. A massive object creates a gravitational field, G, a vector field around it, and another massive object in this field accelerates with an acceleration which is equal to G at a given point. And with the Einstein's gravity, just a perspective change, a shift, a total paradigm change occurred. And what we have is a massive object curves the space-time, and another massive object on this curved space-time follows the shortest possible path, basically. And excuse me. For the Newton's gravity, excuse me. Honestly, I wonder. benim için ilginç bir şekilde zorlaştı ama okay. So yeah, I have some hardness to view the titles, but if you can see, no worries. But starting with the Newton's gravity.
We can see the titles, Tahsin hocam.
Okay, very nice. But when I switch to some annotations, you cannot see the title, right? You see something appearing here. So no worries. I always see this one, but yeah, just let me move to the ingredients of the slide. Newton's universal law of gravitation. Thanks for the feedback, by the way. Newton's universal law of gravitation. We all know basically in this form, yeah, just two masses interact with a force dictated by this law, and Newton's second law gives us the motion basically, and equivalence principle says that yeah, inertial and gravitational masses are the same. So what we have is the acceleration is the G field equal to the G field created by the mass. And moving to the discussion in gravitation, Newton's gravity, continuing the discussion in Newton's gravity, basically gravitational field of V of the mass m is basically gravitational force per unit mass, and defined like this. Defined like this, and yeah, this is in analogy with the Maxwell's law. Remember, the Maxwell's law has this form where the electric field is given like this, and what we have in analogy is for the gravitational Newton's gravity case, we have this, yeah, just analog of the Gauss's law, if you want. And acceleration of any mass in G is just given with the vector field. G is given like this, as I mentioned in the previous slide also. So you can define the gravitational potential, right? You can define the gravitational potential as the gradient of the potential gives you the gravitational field, the G vector field. And so for a point mass m, we define the gravitational potential as like this. And in terms of the potential, you have the Gauss's law in this form. And acceleration of any mass in G is given in terms of this gravitational potential as gradient of the potential, negative of the gradient of the potential. And moving to the Einstein's gravity, and yeah, just creating some analogy with the Newton's gravity perspective that we have discussed in the previous 3 or 4 slides. And what we have here as the law, the Gauss law dictating the gravitational potential, yeah, just or the source creating the gravitational potential in this form is the basically Einstein's equations. And in the Einstein's, yeah, just going step by step is basically massive source with density rho creates the gravitational potential phi in this form in Newton's gravity. What we have in Einstein's gravity is basically energy momentum force. The mu creates the space-time curvature, the Riemann tensor. And the Riemann tensor contracted once gives you the Ricci tensor, and the Riemann Ricci tensor contracted once gives you the Ricci scalar, and basically G mu is the metric, and T mu is, as we stated above, the energy momentum tensor, and G is the Newton's gravitational constant. And basically moving to the acceleration or the motion in the gravitational field, this equation gives you how the object in the gravity field of another object accelerates in the Newton's gravity case. And for the Einstein's gravity case, what we have is basically any object having the energy momentum follows the shortest distance path on curved space-time. And basically we have geodesic equation giving us this shortest path, and basically, yeah, these two equations are the analogs for the Newton's gravity case and Einstein's gravity case. And moving to the description of the elements appearing in the Einstein's gravity and the metric. Basically, the first element that we shall discuss. What is the metric? Is basically metric community is the fundamental object which determines our space-time, and community is basically the line element associated with the infinitesimal displacement vector. So in 2D flat space, what we have as the metric is, yeah, just this is the line element infinitesimal distance between 2 points given simply the Pythagorean theorem, and what you have as the metric is this diagonal metric having these elements. And what G mu nu is basically the element counted with these indices. And 2D curved space-time of a sphere is given with this metric that you can feel when you want to find an infinitesimal distance between 2 points on a unit sphere, whose surface is yeah, just parameterized with theta and phi, basically. And moving to the space-time metric case, we up to now discussed the space metric, and space-time metric is you, yeah, just associated time to the space, and you have 3 plus 1 dimensional flat space-time, which we call Minkowski space-time, represented with this metric eta mu nu. Yeah, just changing the name G to eta, and it has such a form where time is, yeah, just different from the space part with this minus sign appearing here. And yeah, time has a different characteristics as part of this space-time compared to the space part. And 3 plus 1 dimensional constant positive curvature, maximally symmetric space, excuse me, maximally symmetric space-time, which we call the Sitter metric, has such a form. So what, okay, just give a look. This is the flat space-time, and moving to the Sitter space-time, yeah, we have this factor, yeah, just creating the positive curvature, maximally symmetric space-time nature. And for the negative curvature, maximally symmetric space-time, yeah, just there is a typo here. I shall put anti-de Sitter has such a form here, time appearing as a coordinate in the overall factor. Instead, we have Z for the anti-de Sitter case. And moving to step by step, more, let's say, yeah, rather new space, yeah, space-time as an object new, but moving to, yeah, just one of the important discoveries of Einstein's gravity, which is the Schwarzschild metric. It is a 3 plus 1 dimensional spherically symmetric curved space-time representing the space-time of a black hole, basically, and it has such a form, and yeah, just providing all these 4 metrics for comparison with the flat case, moving to the black hole metric in one slide, basically. And moving to another object that we shall define in Einstein's gravity is the covariant derivative of a vector V mu. And yeah, to define the covariant derivative, yeah, just you need to have the Christoffel connection appearing here. And why there is this Christoffel connection term? Basically, basis vectors are coordinate dependent and changing at every point in space-time. So since the basis vectors change at every point in space-time, you need basically an adjustment, and this Christoffel connection is provides you the transformation between point to other point in terms of as you may guess, the derivative operation compares the vectors in two different points, and basically if the coordinates are changing, you need to have an adjustment between the coordinates. And the example of the polar coordinates is basically just having this, let's say, 2D surface parameterized by r and theta coordinates, and what you have in 2 dimensions is a vector v is r is the magnitude, r hat as the unit vector representing the vector, and what you have is v mu is r0 as component, and the covariant derivative or the Laplacian, excuse me, the Laplacian has this form basically, and when you hit the Laplacian on v, you see that the derivative hit on the vector part, the unit vector part, and in Cartesian coordinates, what you have as from point to point, nothing changing in terms of the coordinates, but for the polar coordinates, r vector changes from point to point, and that change is in moving theta direction. That change is theta in theta hat vector direction. So the covariant derivative basically in theta direction, basically, as I said, these indices is just counting the coordinates, and we selected a specific index theta, and hitting to the general vector v mu. What we have is basically derivative hitting to r gives you a 0, but you have a contribution coming from this Christoffel connection part due to the change of coordinate, change of r coordinate from point to point. So the presence of Christoffel connection is just related to the coordinate change, and these Christoffel connection gives us gives us the mathematical object to define the curvature. Basically, Riemann tensor defining the curvature of the space-time or the representation of the curvature is basically can be defined in terms of the Christoffel connections as in this equation. Basically what we have is Christoffel connection has one derivative in the metric, as we, let me remind you, Christoffel connection has one derivative in the metric, and basically the Riemann tensor then has two derivatives of the metric, and Ritchie tensor is this contraction. Basically what you have is you are summing up the first up index and the third index, and curvature scalar is basically another, or the Ritchie scalar is another contraction of the second and third indices with the inverse metric like this. For the Newtonian limit, what we have is slowly moving particles compared to the speed of light. How we define the Newtonian limit is basically particles are slowly moving, and what we have is a just weak gravitational field. Gravitational field. You are perturbing the Minkowski in a sense. H mu is very small, and time-independent gravitational field is the other requirement as Newtonian limit. And what you have is this Christoffel, this geodesic equation yields the Newtonian case, and this Einstein's equation gives you the Newtonian case basically in these limits. Basically, just as you expect and as you must require in the domain that Newton gravity really works well, you recover the Newton's gravity out of Einstein's gravity, basically. And the phi is, the gravitational potential field is given by the 0, 0 component, time component of this perturbation appearing here, basically. And yeah, just building up step by step, and we come to the action and the spectrum of the theory. And for Einstein's gravity, we define the theory with this Einstein-Hilbert action. And if you take the variation as in the classical mechanics sense, you have the Einstein equations like this, but we haven't introduced the sources, the matter part, due to that we have 0 on the right-hand side. And one can consider this theory as the fluctuations of massless spin-2 field H mu nu around the background G bar mu nu, solving the Einstein's equation. So you can divide the metric up into 2 components, a background and a perturbation on that background. And the non-interacting theory, the linearized level of the theory, can be found by looking at the, just as I just said, linearized order in H mu nu, and in flat background, H mu nu satisfies this equation basically, and big cage. Just like in the Maxwell's theory, classical electromagnetism, you have a gauge freedom, and we fix the gauge for the perturbation, like the simple form resembling to the Newton's case, as you may realize. By the way, if my connection creates some problems, please warn me to switch to another possibility. And successes of the theory is precession of perihelia of planets, and gravitational effect on light, bending of light, gravitational redshift of light, gravitational lensing. All of them are the successes of Einstein's gravity, and detection of the gravitational waves is recent time great triumph of the theory, and basically makes us to look at the universe with totally different vision and new. Hopefully we can have some. In the coming years we can probe with LISA and just other gravitational wave detectors, introduction of other gravitational wave detectors. What is I really wish and look for is to see some signals from the Big Bang time, and to hear about the Big Bang, to look at the Big Bang with the gravitational waves eyes, and it will provide a marvelous info, hopefully in the coming decades, and just so totally new perspectives pops out to look at the universe. And so Einstein's gravity basically is not just totally absolutely let's say out of some problems or some absence, what I mean, not perfect in a sense. And what are the problems of Einstein's gravity? Honestly, I cannot see the title. I'm trying to title from my mind. And the problem of Einstein's gravity is basically Einstein's Hilbert action does not provide a theory which is not generalizable. What I mean is, in the quantum field theory sense, just has a problem of predictability. What I shall say is basically to make it renormalizable, to get rid of the infinities popping up in the loop calculations. You need to introduce additional terms. And basically what Stella found in 77 and 78 is basically the Einstein theory becomes renormalizable with the introduction of new higher curvature terms. And with the introduction of these terms, it becomes, it starts to have a better feature of renormalizability, but it lost its unitarity. In one sense, this theory in total is which is the quadratic curvature gravity theory. Just that you can make up in 4 dimensions at the very first step. It is some theory which is good, but it some bad feature introduced, it loses the unitarity nature. I will discuss more if the time permits about the unitarity and the effective, also there is some part in the coming slides also. Effective field theory perspective is basically if you move to higher energies, higher curvature and derivative terms should be introduced to make theory at the every new energy frontier to make theory renormalizable for every new energy frontier, and so moving more and more loops, let's say, in the quantum field theoretic calculations of gravity. And what you have is 4 dimensions. So I discussed the thing for the 4 dimensions here. For 4D dimensions, you have another possibility to add at the second curvature order, and this is the Gauss-Bonnet combination that you can add to Einstein's theory in addition to these 2 terms. And if you move higher and higher energies, you need to introduce the 3 curvature terms, and in addition to 3 curvature terms, now you can also introduce the covariant derivatives of the Riemann tensor and its constructions, basically rank 0 constructions in every possible way. So your in principle your possibilities is limitless and goes to infinity as you go to higher and higher energies. Let me be quick if you want. A possible explanation of the accelerated expansion of the universe is just can be provided by modifying gravity, and expansion rate of universe is increasing, and possible solution is modifying Einstein's gravity in the infrared, the cosmological constant infrared or large length scales, if you want, at the length scales of the universe. And cosmological constant is the first thing that you may add to the theory, and just this simplest modification provides you the standard cosmology that we have today, basically, or you may introduce a small mass to the graviton, and gravitational force has a finite range if you have this small mass introduction due to this Yukawa kind of term. Basically, what you have is if you introduce a small mass, the 1/r² type of behavior has this exponentially decaying part in large scales, and you adjust them, just as you may guess and expect immediately, this mass should be very, very small, and it starts to affect at the very large length scales of the universe. And okay, why we are changing the Einstein's gravity? It is not renormalizable, so accelerated expansion of the universe requires to modify it. Just what we are working on is basically modifying gravity, but why is the thing that we are discussing now. Basically, to understanding anything, you change it, reshape it, look from away. This is the thing that you do from the our babyhood or our childhood. What we do is, if we encounter some object, something, we try to understand it by just playing with it. And what you are doing with modifying gravity is basically playing with the theory to create different features, basically to understand the Einstein's gravity better and better. So this is the main motivations to modify it. And what we have done up to now with this introduction is we discussed the Einstein's gravity in comparison with the Newton's gravity. And in addition to that, we just try to have some motivations to modify Einstein's gravity. And after discussing these motivations, let's move to how to analyze modified gravity theories. Okay, you modified the theory, but yeah, just what shall we require? What good features the modified theory should have is the thing that you may first ask, and what can be the next theory, next gravitational theory as good as Einstein's gravity may be the question. And so if you modify the Einstein's gravity, a generic metric-based gravity theory can be represented in this form. Yeah, just this is the title of the talk, basically. And higher curvature or derivative gravity theories can be generically represented with this action. And you have higher curvature, basically, if you get rid of these covariant derivative terms, the higher curvature gravity. But if you keep them, you have the higher derivative gravity theory, basically. And the question is, for this theory, is there a maximally symmetric vacuum? And if it is so, what is the effective cosmological constant? Is the first thing that you may want to ask. So you want to the theory have some good features, and the first thing that you may want to ask is basically the very simple space-times that are solutions of Einstein's gravity, whether they exist or not, and if they exist, how they can be represented in terms of the curvature. And the first thing that you may observe when you analyze the theory is the derivative terms do not contribute to the maximally symmetric vacuum, since they will yield the covariant derivatives of the metric tensor at the level of the field equations, which vanish by the metric compatibility. So any covariant derivative hitting to the metric should identically vanish, and due to this metric compatibility nature, these derivative terms do not affect the maximally symmetric background. And how you figure out this? How can you calculate the maximally symmetric background and its cosmological constant, the curvature of the maximally symmetric background? Basically, you may use the equivalent quadratic action ideas, and basically, okay, up to now, yeah, just we discussed the very basics, but I am now trying to introduce a concept that you can analyze this kind of theories, and this concept is the equivalent linear action concept, and basically, equivalent linear action is yeah, just only the terms involving the Riemann tensor, but not its covariant derivative, are relevant for finding the vacua. And let us denote this part of the action as like this. So you get rid of the that covariant derivative terms, and you have an action which is just a function of Riemann tensor and its contractions, basically, and can be formed as the contractions of the Riemann tensor at any order, any Riemann tensor order. And sorry, and we have also gotten rid of the inverse metric without loss of generality, and taking independent variable to be r mu nu up and alpha beta down indices that could stand for the Riemann tensor, or if once contracted the Ricci tensor, if twice contracted the curvature scalar. And basically, the Einstein-Hilbert action in this language reads in this form. So no need to, you just need the Kronecker deltas, and without the metric, you can deal with this, yeah, just accept term, right? Deal with the action, basically, due to that we prefer this up, up, down, down form of the Riemann tensor. And how to figure out the cosmological constant, or the constant curvature of the space-time. Basically, yeah, to go to the equations of motions, you need to take the variation of I, and when you take the variation of I, you obtain this part when you have an action where the covariant derivative terms are deleted basically. And for the maximally symmetric spacetimes, if you put the maximally the specific form of the Riemann tensor for the maximally symmetric spacetime into this equation, what you end up is these all these covariant derivatives hitting on the derivatives of the action with respect to the Riemann tensor, and what was remaining is basically this part having this form, in fact, and where the terms are calculated for this maximally symmetric value of the Riemann tensor, having this specific form in terms of Kronecker deltas, and this lambda is the cosmological constant, or it gives the constant curvature of the space-time. And basically, just as I said, what we are doing, the aim is to create a way to calculate the specific solution of the most complicated theory. And we are going step by step. We derive the equation of motion, right? We derive the equation of motion by taking the variation here. And we put our basic form for the maximally symmetric spacetime. And then we have some specific objects here calculated for the maximally spacetime, these first derivative of the action and the action itself. And notice that in the vacuum field equations, the information on the functional form of the Lagrangian enters the field equations through only two background evaluated quantities. And these, therefore, if these two quantities are the same for any given true gravity theories, then those true gravity theories have the same maximally symmetric vacua, namely their effective cosmological constants are equal. So honestly, just looking at the time limit, at least, just moving to other stuff, what may be the aim of this talk is to understand this equivalent linear action principle. And the nice thing is, okay, where the specific theory comes in, where the specific nature of this action comes in, maybe the question to determine the maximally symmetric space-time solution of the theory, basically with these factors. And if true theory has same result when its action is calculated with this maximally symmetric space-time for, and when first derivative of the Lagrangian calculated with this maximally symmetric space-time form, if these two are the same, then these two theories having these two quantities are as the same, should have the same vacua, same maximally symmetric vacua, and basically, and the simplest theory that you can cook up with these configurations is the this Einstein-Hilbert form. What you have is, all these are basically the Kronecker deltas that you have here. Only this Riemann tensor is the quantity having some variable nature, providing the let's say the R in the Einstein-Hilbert action, and we call this theory as the equivalent linearized action. So then, for a theory defined by F R mu nu alpha beta, one can determine the vacua of the theory by performing a first-order Taylor series expansion around yet to be determined maximally symmetric background, as in this form. And to get the effective cosmological constant of the vacuum or vacua of the most general gravity theory, all one needs to do is the first-order Taylor series expansion of the generic theory in the Riemann tensor and construct the equivalent linear action. Basically, Taylor series expansion that we learned in the calculus course in the first freshman year will give us the way to find maximally symmetric solutions of a theory. So, and excuse me, and defining data out of this first derivative calculations, which shall has this form in terms of Kronecker deltas. And if you contract with the Riemann tensor, you have the Ricci scalar, and what you have at the end is a cosmological Einstein's theory. Why I say cosmological? Basically, these cosmological constant term and these kappa and this cosmological constant for the linearized theory can be determined from the first derivative term and the calculation of the Lagrangian with the maximally symmetric space-time Riemann tensor form in this form. So if you basically do these calculations, what I mean, if you calculate this term and if you calculate this term, then you end up with the solution, maximally symmetric solution of the theory that you have, whatever theory, how complicated theory does not matter basically. And vacuum from this equivalent linearized theory is basically as simple as Einstein's theory, because it is cosmological Einstein's theory, and the cosmological constant of the theory is equal to this Bayer cosmological constant appearing in the action. And in terms of F bar and zeta that you calculated from the first derivative of the action and the Lagrangian itself is given like this. So what we have at the end is basically as a discussion or calculation. This is all thoroughly equivalent to taking the variation of the action, putting the maximum symmetric background into the equations of motion and doing the calculations. Instead of doing that, what you shall do is you shall just calculate the equivalent linear action. Why we discuss this? Okay, so I am already out of time for 1 minute and trying to just collect everything together. Unfortunately, at the 27th slide, due to being a bit, excuse me, till to the 4:30, or I have, how much minutes do I have?
I think you have 15 minutes left.
Perfect. Okay, I thought that it is 1 hour lecture. Due to that, I was sad about it. So I have plenty of time then in terms of discussion. Okay, not plenty, but just plenty compared to 4.
We may eat 5-10 minutes from the break as well if it needs to be.
Okay, thank you very much. So what we have learned in this section, we have learned a way to analyze modified gravity theories. A way to analyze modified gravity theories, what I mean is to find maximally symmetric solution. Maximally symmetric solution, just like the case of Einstein's gravity. And these maximally symmetric solutions are very important. The Minkowski space-time, the flat space-time, or the de Sitter space-time, the anti-de Sitter space-time, remember, they are the simplest looking metrics, right? They are the simplest looking metrics, and they can provide background for your field theory calculations, basically. Field theory in Curvature space-time calculations, and just the standard quantum field theory calculations in Minkowski space-time. So you really want to see whether your theory has a maximally symmetric background, and we learned a way to find it by simply not delving into the thorough details of taking the variations and putting the Riemann tensor in it and calculating the cancellations and things like that. What you shall do is you shall calculate just this object and this object, and basically you obtain Einstein's cosmological Einstein's theory with this action, and using this action, you find the cosmological constant, and you see that, okay, I have a maximum symmetric background, and if this lambda 0 is defined, and you found the cosmological constant. And so you may want to have unitarity analysis, you may want to have spectrum analysis. For all of them, what you must do is, okay, this is the linear level. What you shall do is, to look at the spectrum, you shall look at the second order in Taylor series expansion of the Lagrangian and the action, basically. So the basic idea is, okay, you shall use this simple idea of equivalent linear action by moving higher and higher terms in that Taylor series expansion to figure out different features of the modified gravity theory. And basically, with that kind of analysis, how can you build up as a theory? And as an example, let's discuss the Born-Infeld gravity in 4 dimensions. So Born-Infeld type of gravitational action has such a Lagrangian density, basically. And this Lagrangian density has a determinantal form where you have the metric added to an a mu nu rank 2 tensor, which is built up with the Riemann tensor and its contractions. And you don't want an arbitrary modification, right? You want to have this theory has some nice features resembling to Einstein's gravity. And what shall be these nice features is basically, yeah, the first 3 items that you may want to impose can be, or maybe is, the theory reduces the cosmological Einstein's theory at the lowest order in the small curvature expansion about the flat space or anti-de Sitter or de Sitter space times, and to the Einstein-Gauss-Bonnet theory at the quadratic order. So what you want is at the lower energies, you want to have the well-working Einstein's gravity. Yeah, just the Einstein-Gauss-Bonnet term or Einstein-Gauss-Bonnet theory is, for example, if you like and study the string theory as the quantum gravity possibility or theory that you have in your hand, then what you expect, or asymptotic safety, what you expect at the second order, at the quadratic curvature order is, yeah, yeah, for asymptotic safety, the other terms also there, definitely, because you don't care about unitarity at every order. But for string theory, at the second order, what you expect is Einstein-Gauss-Bonnet theory at any d dimensions. And if you restrict yourself to 4 dimensions, what you see is basically Einstein theory. Yeah, and nothing should be added up to at the quadratic order, because it slows down the unitarity, although it's increasing renormalizability of the theory, or yeah, just providing the better feature of the renormalizability. Anyway, so this is the first that can be required. Yeah, obtain your best theories at low energies. If this is the any energy order theory, because in principle you have any order out of this determinantal square root of determinant Lagrangian density. And the theory describes only massless gravitons around its flat or ADS vacuum at any finite truncated order in curvature expansion or as full theory, namely if all powers of curvature are included. So Einstein theory has only massless gravitons as excitations, as spectrum in this around this maximally symmetric backgrounds of ADS or this flat background. So you want this Born-Infeld type, some complicated theory also behaves as a spectrum as in the case of Einstein's gravity. Sorry. And the theory has a unique viable vacuum is just like the Einstein theory. Maybe the other thing that you may want to require, and namely there is a single maximally symmetric solution for which the massless spin to acceleration about this solution is unitary. So basically what you are requiring is the all good features of Einstein's theory as maximally symmetric solutions, uniqueness of maximally symmetric solutions, and unitarity of the spectrum in this maximally symmetric backgrounds. And basically, we are requiring this property not only as a full theory, but at every curvature order. And yeah, what you have created is a really demanding set of requirements, and let's see whether we can construct this kind of a theory and how to construct this kind of a theory just based on the analysis that we discussed in the second section. So let's discuss the traceless-Ricci tensor and Weyl tensor as the objects that will determine the A mu tensor appearing here. And traceless-Ricci tensor is defined in terms of Ricci tensor and curvature scalar.
Hocam, tek ben mi dondum?
Ben dondum mu şu anda? Onu
ben de duyamadım, geri geldi şimdi.
Ben dondum. Siz de dondunuz mu?
Yani şu anda yani eğer internet internet connection is unstable diyor ama çok sık gidip gelmeye başladıysa isterseniz şey yapabilirim.
Like
connection
5 more minutes. If you want to slowly wrap it up, but it's fine.
Okay, thanks. And just let's have this 5 minutes with this connection. Definitely better.
Sure, no problem.
Weyl tensor is defined in terms of Riemann tensor and its constructions. And basically, this for the BI gravity theory with unique vacuum and massless graviton can be constructed as in this form by starting any A mu form that you can construct with second order constructions of the traceless-Ricci tensor, the Weyl tensor, and the Ricci scalar, basically at second order, can be, basically, excuse me, has this form. What I mean has this form is, okay, what you shall do is, okay, you start with the most general A mu, and you put the requirements on it, and what you end up is basically you end up with the presence of this two tensors as constructions of Weyl tensor and Ricci tensor and Ricci tensor and traceless-Ricci tensor, and also this total constructions of these these three objects and these two tensor part, rank 2 tensor part comes from the metric itself. So this is the A mu that you can have at the quadratic curvature order of A mu, satisfying the very nice features of the Einstein's theory. So although the theory is infinite order in curvature, it has two ADS vacua for lambda 0 smaller than 11 over 16 gamma and satisfying lambda 1 over gamma. So basically, your theory has the nice feature. So what I mean two vacua, basically DS or ADS. So one DS, one ADS solution, and the spectrum of the theory consists of only a massless graviton, which is the three-level unitary, about only one of these ADS vacua at any truncated order. So you look at the theory at second order, third order, fourth order, at every energy scales. You work on the meaningful theory of that energy scale at the truncated order corresponding to that energy scale, and what you end up is basically a nice theory which has the same spectrum and similar vacuum structure as the Einstein's gravity. And the okay, so basically with high curvature terms, you can have theories in terms of spectrum and vacuum as nice as Einstein's theory. So at the point of just more or less having reaching to the announced limit of the time, let me state what we have learned, and then afterwards let me quickly move through to the end by giving a view for the remaining part. So what we have done up to now is, okay, we want to modify Einstein's gravity. Why we want to modify the Einstein's gravity? Basically to explain some observations, just like the accelerated expansion of the universe, or to make the theory renormalizable, to quantize the gravity even. Just what I mean, quantum gravity theories just dictates you to modify Einstein's gravity in higher energy scales with the higher derivative and higher curvature terms. So there is a well-defined motivation to modify the Einstein's gravity, and a well-defined motivation to modify it with higher curvature and higher derivative terms. And what we are doing is basically, okay, if we modify the theory, how to analyze the theory, how to understand the basic features of the theory in terms of vacuum, which is basically the maximally symmetric solutions of the theory, or if we modify the theory, will it resemble to Einstein's gravity at the lower energy scales or higher energy scales? And we discussed a tool to do this, okay, to analyze the theory, which is equivalent linear action. And also equivalent quadratic action will provide you to analyze the theory with at the spectrum level. And with these tools in hand, we focus on a specific theory which is motivated by the Born-Infeld modifications, which is motivated by the Born-Infeld modifications of Maxwell's classical electromagnetism, basically. And Born-Infeld modifications are motivated to have, let's say, just self-energy problems of the classical electromagnetism, basically. Using that kind of modifications in classical electromagnetism in the gravitational setting, and this square root of determinant action resembles the resembles with the special relativistic particle action. So with these modifications, let's have such a kind of a modification of Einstein's gravity, and will this modification behaves nicely? And what we are doing is a bottom-up approach. From bottom, having our base as Einstein's gravity, and step by step modifying it, not like the quantum gravity perspective of high energy theory, having a very well-behaved quantum gravity theory at the Planck scale, and trying to see what's happening at the lower energy scales and how to matching with the Einstein's gravity at the low energy scales. What we are doing is basically, okay, let's start with the Einstein's theory, and step by step try to modify it, look at some specific modifications, and trying to look at whether they can be made nice behaving theories, just like the Einstein's theory. Whether they can have the nice features of the Einstein's theory is what we are searching for. And with this action, yeah, we have some marvelously behaving theory at 4 dimensions, just like Einstein's gravity at any curvature order. So, yeah, trying to say something about with the bottom-up approach for the modifications of Einstein's theory and how they can be made well-behaved. And so, in 1 or 2 minutes, so you can define really well-behaved theories by using the tools that we discussed in this section in the Born-Infeld setting, which yeah, these tools can be used in any kind of setting, and this Born-Infeld setting is really interesting, especially in 3 dimensions. Born-Infeld modification of new massive gravity, which is related to the massive gravity theories as a limit. So it really has some interesting connections with the massive gravity theories widely discussed, and also the Bolvere-Desargues ghost is absent in the Born-Infeld modification of new massive gravity in 3 dimensions also. This is the 4-dimensional analog. And when you have these theories in hand, another question that you may ask is, what can you say further about their solutions? This is the, okay, maximally symmetric solutions we already discussed. But what else that you can determine out of this complicated action? What we have discussed is start with these kind of metrics. Remember, this is what we have done in the Newtonian limit also. We have the background also in addition to some h-minute perturbation. You may think as the h-minute perturbation has a specific form with these 2 lambda 1 forms and a metric function v, and this Curvature metric satisfying these nice behaviors, yeah, nice properties, lambda. You define a zeta 1 form here out of the covariant derivative of lambda, and this zeta, excuse me, xi have some nice behavior in terms of contraction with lambda gives you 0, and basically v metric function has such nice property and a very crucial property, and this Curvature matrix belongs to the Kundt spacetimes, and when you study these Curvature Kundt class of spacetimes as solutions of these generic theories, what you end up is basically, yeah, let me state this theorem, or let me state this outcome, corollary of this theorem. So, then finish. ADS waves are members of KSK class, and ADS waves are solutions to any higher derivative theories. What I mean is, ADS wave solutions of cosmological Einstein's gravity, this theory, and ADS wave solutions of quadratic curvature theory, basically this yellow and this green theory solutions, ADS wave solutions. We call the Curvature metric form where the background is ADS as ADS wave, and that Curvature metric form solutions of Einstein's gravity and quadratic curvature gravity nicely solves this higher derivative theory. Yeah, this is okay. To understand a gravitational theory, you look at its solutions. Basically, finding solutions is a very important thing. For example, Schwarzschild find the solution and change, yeah, thoroughly our perspective to look at the universe, right? Just we are now looking at the collision of the black holes, and basically black holes are represented with this Schwarzschild metric, right? So solutions are very important, and basically Curvature-Kuhn class of metrics are a very important class of metrics, which are the solutions of higher derivative theories if they also solve Einstein's gravity and quadratic curvature theory, basically. So let me stop at this point. Oh. Exactly, this is a very nice point to stop, which you also want and which we shall need definitely. Okay, thank you very much, and sorry for being a bit late at the order of 10 minutes, and sorry for being late at the very beginning also.
No problem. It was a great talk. Let's have the questions in the Slack channel later, as we don't have much time left. Okay. Tahsin, I'm gonna stop the recording.
Okay.